Well, good morning, everyone. My name is Travis Willett Geis. I'm currently an employee of the Aerospace Corporation here in Colorado Springs, but I'm giving you this presentation because before this job, I spent 8 years at AFRL as a AI&T engineer, a systems engineer, and sort of touching all phases of CubeSat development. So I have done it for a while. I've done it a number of times. I've broken a number of things, and at least for now, hopefully that makes me qualified to speak a little bit the fun parts: assembly, integration, test, GSE, and some of environmental testing. So without further ado, let's get into it. Assembly, integration, and test is 3 words. 2 of them feel redundant, assembly and integration, but they are distinct and unique, and we'll talk about both. And then testing is sort of the way that we prove assembly and integration is working and doing what we intended our system to do. So if you have seen any of the systems engineering presentations or have been exposed to systems engineering, you'll see this kind of concept presented in a number of ways. The V is a pretty classic one, where to do a CubeSat mission or any sort of engineering enterprise, someone has come up with a proposal of what we're going to do. What should the system do? We want to take a picture of Zimbabwe, or we want to measure how much RF is coming out of a cell tower in Alaska, something like that. And you've put that together into a system design. So you've kind of gone down this systems engineering path on the left side of the V, where you've defined what that mission actually is going to do, what it needs in order to be able to do that. So if you're going to take a picture, you need a camera. That camera needs electricity. You got to point that camera at something, et cetera, et cetera. And that should get distilled all the way down to its lowest level of design, to where you know every single component that is going to be needed as part of the system in order to accomplish that original objective. Assembly, integration, and test is the entire right-hand side of the V. It's taking all of those distilled components at their very lowest level, and we start to assemble, meaning we put them physically together, integrate, meaning we put them both electrically together, mechanically together, and softwarely together, and start building subsystems, systems, and then even systems of systems if you have multiple things like a ground system and a space system, in order to prove that what we're building meets that original intent. And we prove that by testing, by running a unit verification at the very lowest level. So if I need a resistor that's 100 ohms, I want to measure it and prove that it's 100 ohms. If I need a camera to take a picture that is so good, I need to take a picture and prove that it's so good, prove that I can power it, prove that I can point it, et cetera, et cetera. So the right-hand side is a lot of fun. It's where you get to test things, it's where you get to break things, it's where you get to actually get hands-on hardware, but it's only as good as the work that you did on the left-hand side. Very typically, and every single one of you, if you get to the phase of integrating and testing a spacecraft, will realize that you didn't do the left side as well as you could have. You didn't come up with as good a system verification plan as you could have. You didn't plan out exactly every component that you needed in exactly the right way. And that's okay. We present this as a very linear flow, but in reality, AI&T is continuous, it is iterative, it is a spiral, it is a mess, and it's how we sort of find those missing things, and the tests are what tell us we don't have quite the resistor that we needed, or we don't have quite as good a camera as we needed, or maybe that camera is great, but we can't actually power it. So it's continuous, it is iterative, and the biggest piece is both proving that the system does what you intended it to do, but also to teach the team, you all, that the system is going to do what you built it to do. You just might not have done that correctly. So the great part about engineering is that these components behave exactly as they were designed to do. You just might not have designed it correctly. So we can use the assembly, integration, and test process to prove that out. It's not a bad thing to fail tests and to find ways to improve the system. It's just what the process is all about. Nothing is perfect. And this is why we do this phase. If you had engineered it perfectly, you wouldn't have to test anything because everything would just work. So the point of AI&T is to verify all of these interfaces that you documented and designed, and you did a really, really great job of writing all your ICDs and writing all of the test plans. So it's just verifying, making sure things fit together, making sure electrical signals are what they need to be and that they are compatible with the thing they need to talk to, and making sure it can power on and actually do what you need. So we have a really cool flowchart here on the right of kind of how you take the requirement specification. So say I need a camera that takes a picture that's good, and then I can actually go through a very formal process of reviews, which you all should be doing now, to say, okay, if I need a camera this good, can I just go buy that? Is there something out there in the world that takes a picture that good? I can just buy it. I can use money instead of brain and solve all my problems. Or do I need to go actually design something? Do I need to buy an actual focal plane array and lenses, and maybe I need to make a new kind of glass because I need the best resolution I could ever imagine in some atmospheric condition. And so that's where you can get into this make versus buy decision, and you start kind of going down what are identical intents in the reviews and the integration and the testing, but slightly different approaches, how far down that V you need to go. Do I just need to verify that camera is okay, or do I need to verify all the subcomponents of that camera? And we do that through the unit testing, the subsystem testing, and the system testing. We then put all of that together to this satellite that we're talking about that hypothetically is taking a photo. We run through what are called 5 tests that we'll get to at the end of the presentation to show that the whole space system is going to do what we need it to do. Here's what it looks like in reality. This is one of the satellites that we worked on at the Air Force Research Labs called VPM, or the Very Low Frequency and Particle Mapper. This is what the integration and test process looks like kind of towards the end. So you can see we have everything laid out on this table, and it's super messy because we've been changing harnesses and we've been learning that our electrical signals aren't quite right, and we've been learning that we need a different battery controller board, or we need a new switch or something. So this is called the flat-sat phase of integration and test, at least for satellites, where you can see all of the interfaces literally laid out in front of you. It's not all folded up into a box. So it's a really great way, like your system block diagram that you might be working on very early on, where you say, okay, the batteries are going to connect to the regulators are going to connect to the switches are going to connect to the radio, et cetera, et cetera. You literally can physically lay that out as close as possible to your diagram, so everything sort of logically flows as you do your engineering. This gives you access to probe things, poke things, understand what's going on electrically. You can see our little mounting brackets and things. We're learning what the right way to orient things, how best to sort of package this all together when we move it over to the right side, where it's an actual integrated satellite, and is much, much harder to debug and diagnose, because this whole process is debugging, testing, and understanding what's happening. So we take this large flat sat where we have every single component of our spacecraft. We can test some things, but we can't test everything. This is inside of a lab, and so we don't have a very good sun inside of our lab. So in order to test that the solar arrays work, we need to wait until it's more integrated there on that bottom right. To test something like the radio, we can see we have a little patch antenna hooked up there. We can test that it emits radio frequency, but we might not be able to test that it performs its whole over-the-air communications test. So down here on the bottom right, where we have radio with the flight sticker on it, we can see that that's hooked up to coaxial cables instead of an antenna. And that's how we can simulate and actually perform radio frequency testing, but without the full path. And that's something we have to do differently. Getting into the phases, like I said, there's assembly, integration, test. Assembly is really the act of the Lego kit, of turning this whole mess here on the left into what's still a little messy, but much more clean, integrated, and at least fits in a CubeSat dispenser so it can go to space there on the right with its solar panels. At this point, where I think most of you are in your CubeSat journey, you have to plan. The whole exercise of decomposing all of your requirements and saying, I'm going to do this as a 3U CubeSat. Everything needs to be planned to fit into that 3U volume when you actually assemble it. You can't have, 3.25 view where you decide, well, I'll just kind of lump something here on the side because it didn't actually fit in the end of the day. So very typically we'll sort of get through that preliminary design and be like, oh, actually, we're going to need larger batteries, or maybe we need more solar panels, or maybe our antenna is weird and so it needs to either pop out or deploy in some weird way. Planning for this assembly process as early as humanly possible, which means day zero, pick your form factor, is a very, very key element. One thing that is a common early mistake, and I did it myself, was to not plan for disassembly. It's a V, right? It's linear. I test the component and then I bolt it to the subsystem, and then I bolt the subsystem to the system, and then I put it in the dispenser and it goes to space. More frequently, it goes the opposite direction. You pull it back out of the canister and you have to take the antenna off and you have to pull back in. So very, very commonly what goes in will come back out. And so designing for tool access, assembly, disassembly, and being able to sort of get to an integrated phase, find something's wrong, go back, figure out what that is, fix it, and then resume the process is extremely important. So we do these things called dry builds in our little flow chart here on the right, where we've kind of come up with an assembly procedure, right? We've thought how this is all going to go together, and then we try it, and we're wrong. So then we go back to the procedure and tweak a little thing. Maybe we have to move a bolt. Maybe we have to add a new access hatch, something like that. We go back to the dry build and we try it again. Any of you who touch CAD for any reason must do this with the procedure in mind. These cube satellites are extremely small and very difficult for human hands, unless you have a really tiny engineer that you can use. And it's very common to forget that you actually need to torque the bolts and get a tool on them and be able to verify that the bolt is tight and Loctited and unable to back out. Because if you cannot torque that bolt, it will fall out, it will cause chaos, and it will break everything. And so that is something that we very commonly miss, and is excellent to practice in the dry build before it really matters, before it's going into the extraordinarily violent launch environment and everything breaks and your mission fails. Another thing that's common in assembly is we forget connectors, harnesses, that you actually need to be able to plug something in and unplug it. So like your USB connector, once it's mated, is quite a bit smaller than when it's free, and you need that free straight path access to be able to plug a USB in. You can't just start with it plugged in, like throwing your laptop into your bag with something still plugged in. Maybe it doesn't fit. Something that's really easy to forget in CAD, because you just make the mate and it's all good and you plan your route, but you didn't actually plan for it to be able to plug or unplug. And that access is very, very key. So keep that in mind at all times. As you're building your procedures, Lego is the best in the world at simple, straightforward, logical, and easy to follow procedures for three-dimensional mechanical assembly. They do an outstanding job of saying, here's all the parts you need for this step, do this step, and you should have no parts left, and plan for how that's going to proceed into the next level assembly. So we love pictures, arrows, notes. You can't present like too much information in an assembly procedure. If you are the CAD designer, you have to show what you intended for this to be. Is it actually going to be built flat, but then rotated 90 degrees? Am I intending to clamp this to a bracket and then mount that bracket to something? So there's the capturing of the designer's intent in a procedure that is very difficult to do. We also need room to interpret. So as we're the engineer or the technician actually doing the assembly, and we understand what the designer wanted us to do, they want this thing on this bracket, and when they want the bracket rotated 90 degrees, but it might actually make sense to rotate the bracket first and then mount it. And so that's when we do this cyclical process, something that you go back to and say, actually, do this, then do that, because it just makes more sense since this is going to come in next. So all of these things are iterative and a slow spiral towards final assembly, integration, and test. And we do that with dry runs. So you can see here some examples from VPM on the right, where we have our kind of avionics assembly, which is that integrated stack. So we went through a whole dry build of that stack, getting all those spacers the right height, getting all those connectors the right size, very messy stack. And then you take those sort of subsystems, integrate them into that larger structure, which is there on the bottom right. That's our 6U structure. And you can see all the gigantic gaping holes in the side of it for access, for mounts, for being able to both install and uninstall components, which is very, very handy. And we kind of do this to understand, like I was saying, maybe this large battery and ADCS stack that's the black box in the middle, maybe that should be first, and then we build everything around that. That was kind of one theory that the designer had in the procedure, and so we tried that. But really everything connects back to this avionics stack, and it has a humongous spider web of connectors that's going to come off of it. And so maybe that should go in first, and then everything will lay the harness in, install the black box, and then just connect it in. And that's what we ended up doing. So we can use these kind of dry builds to say, all right, maybe my harness is a little too long. Maybe it could be a little shorter, or maybe instead of how the designer thought we were going to run just straight down this bottom wall, maybe I actually need to go up around the black box and down, and I actually need like 8 more inches of harness, which in CubeSat land is enormous. So once you've kind of done this dry build process, you've learned how everything is going to literally fit together in physical space rather than CAD space, because those are not the same space. You can then do that assembly procedure revision. You can check your harnesses. You can do the entire install. And then the final and scary piece is that everything needs to pass a full-up integrated vibration test that we'll hit at the end. That's a very violent and a very scary test for any engineer who has designed something fragile and expensive and something they don't want to break. And so every component needs to be secured so it can't oscillate, resonate, and break. And so often that involves adhesives, which when I said design for assembly and disassembly, adhesives are really hard to disassemble, though not impossible. Loctite, locking fasteners, things that are designed to be permanent, but often we want to be able to undo. And that's a very delicate balance. A big part of assembly, which is extremely complex for much larger spacecraft, that way, school bus size, a little simpler for CubeSat size, but still extremely important, is the ground support equipment. So there's 2 categories. There is mechanical ground support equipment and electrical ground support equipment. And these are all the things that you use for your spacecraft testing, integration, assembly that don't go to space. They are the things that you need to bring with you when you are doing your full integrated test. Can I take my picture, move it to the flight computer memory, downlink it over the radio, look at it in my ground station software, and know that I took the right picture? And often there's going to be a lot of support equipment that's necessary to test that before you're actually in space connecting to a real ground system, et cetera, et cetera. So we break it into those 2 types, mechanical and electrical. Mechanical is usually what literally holds the spacecraft, right? The spacecraft is designed to be floating through space unconstrained, but here on the ground with gravity, it needs to be supported in a way that we don't crush our solar panels, that we don't damage our antennas, that we don't mar any of the coatings or anything like that. So for CubeSats, these are usually just kind of a stand, something like that. This is something that is oft overlooked until we get to the very end and say, oh wait, I need to set this thing down. Similar to the assembly procedures, you're designing the system and you're designing how this is going to go together, how it's oriented. So that's a really good example of, we have a base plate that's there sitting on the table, and we need to bolt everything kind of either down to that base plate or to one of the sides. So you can pretty much build everything on the plate and then fold the walls up around it, which was very, very convenient. And you can see here in this case, we don't even really need ground support equipment as typically used. We're using a table, which technically counts. Towards the end, there are closeout panels, there are several things mounted, including solar panels on that bottom face. And so we need some kind of stand to be able to get that. And that was something that we designed later in order to be able to get there, because we were planning on the base plate assembly. So mechanical ground support equipment is, how do I hold it? You can see here's a relatively complex, but still fixed in 1 dimension stand that Surrey is working on here on the right. It's designed To support everything so you don't drop it, there's a very common example, which we don't show the photo, of a extremely large spacecraft that was mostly mounted on its ground support equipment, but not entirely. Some bolts were not torqued, and when they went to turn the system over, it actually fell off the stand and caused, several $billion in damage. So don't be responsible for that. It's okay to break things, but try to make them cheap. So when you're designing your stand, when you're designing this assembly, keep in mind, like I said, the access in multiple orientations. So how am I going to hold it horizontally, vertically, at a 45-degree angle, at a really weird 33.5-degree angle, because it turns out my screwdriver is exactly this long and prevents me from going either direction. It has to constrain the rotation and translation of the system in all of those axes. So it needs to prevent this satellite being assembled from shifting, falling, harming the technician. Typically we'll have lockout features or inhibit features that actually sort of constrain that or prevent the system from being able to power on while it's in certain orientations, things like that. You have to keep in mind when you're going to use the stand. So is it going to be used only in the clean room during assembly? Is it something that I want to be able to go into a vacuum chamber so I can support my system while it's under test? Is it something that needs to go in a thermal chamber and pass all of the same environmental material standards as this flight system? And that's a very key and important piece. Electrical grounding is something that's very difficult, especially in the state of New Mexico, where it's extremely dry, get a lot of arcing and static electricity. It's really bad for CubeSat systems. Planning for how the entire, you can see these Delrin stands here on the bottom right, those are non-conductive. So if I place my satellite just on those systems, I now have an electrically isolated, very sensitive piece of equipment in a lab full of static electricity. So if I shuffle up and touch my CubeSat, I could actually cause ESD damage to it. So I need to plan a grounding route around that Delrin to the common facility ground. It's also important not to overcomplicate it. We see this a lot of these things are fun and mechanisms are always a good time, especially for mechanical engineers. It's easy to spend a lot of time and money on what could just be as simple as 2 pieces of Delrin on a chunk of aluminum with a grounding strap. So it's important not to overcomplicate it if you don't have to. Lots of lessons learned in the UNP program from that one. Moving things is always difficult. For 1, 2, 3, 6U, a single human is typically able to pick them up and move them around, manipulate them by hand, as long as you have handles or access points that aren't all covered in solar panels. But once you get up to something like a 12U, those start to be much too heavy for a single person to handle, and sometimes even too complex for a 2-man lift or a 2-person lift. So if you need fixtures like crane hooks or the ability to pick it up, translate it, and set it back down, this is something that's oft overlooked. Not overly complex for CubeSats, but as you think about 12U and beyond, as the sort of industry is growing in that direction, that's something that starts to become a problem that wasn't typically the case for this form factor. Designing those interface points for where you can actually contact the vehicle and move it around without damaging very delicate exterior components is a big part of the very early design. You'll see cutouts and requirements changes for those exterior surfaces to be able to accommodate the ground support equipment, not something that's ever going to be used in space. So on the right here is something that we're pretty proud of, our kind of turnover fixture in SSP that we use. It can clamp a 6 or 12U base plate and then be able to rotate on 2 axes to be able to provide access to basically every face of the satellite during assembly. And that's really convenient. We built it to be able to go into the vacuum chamber, into the thermal chamber, and be able to kind of support deployments, anything that needs to sort of exceed the physical volume of the 6U for deployment testing, things like that. So there are often test interfaces that are required, both electrical and mechanical. In the mechanical context, you need some way to mount your system to, say, the thermal chamber, like we've been talking about, or the vibration table. Typically, that can be done in the canister that will be going to space with you, but then the canister needs mounted in some way. So these are often done with either test deployers that have vibration table interfaces like you see here, interface plates, things like that. As with all things, it's easy to focus on the base system, but it's important to consider how you're going to mount it to the test fixtures, to all of the chambers and things that you'll be going through. And that can change dramatically if you have a last minute change in test facility. And that's something we see a lot at AFRL as we do third-party testing for companies in the Albuquerque area. And they'll arrive with an interface plate for one vibration table that they were planning on, but our vibration table is completely different. And so we often need to go remachine or make an adapter, things like that. For shipping, for how you're actually moving and protecting your system during transport from where you were building it safe in your lab to where it needs to go to either NASA or SpaceX or DoD or any small launch company. You'll protect your sensitive, like camera optics, things like that. These are always, always, always red and very obvious and extremely well documented, because if you leave the lens cap on when you launch your camera into space, your PI is going to be very upset. For shipping, this is another nice part about CubeSats is they're small. Up to a 6U will fit in the overhead compartment of most commercial aircraft, including most regional jets. I think we got a 6U on a CRJ, so it doesn't matter. But you can mostly just stick it in a Pelican case if it's properly protected and padded and carry it around with you. For something like a 12U, it does not fit in the overhead compartment. Shipping logistics get more complicated. You either have to find a van or ground transport or air transport that's dedicated like to you in that case, or plan for shipping, which FedEx can do, but it is expensive. Important whenever you are transporting the system to have shock watches, which are sensors that will trip if it experiences a shock of some magnitude, to know if the FedEx guy just chucked your $1 million satellite off of the loading dock, which does happen, or even if you accidentally bang it on the door of the airplane when you're carrying it, that can cause damage to the system within. Electrical ground support equipment is all the same things, but for electrical instead of mechanical. So this is how you interface and test the system while it's on the ground. When it's in space, you're going to use a radio of some kind, either optical or RF. The ground support equipment is how we do that for all of AI&T. So if you remember back to the spider web, a huge part of that was the electrical ground support equipment. It was running down through that table that was sitting on to a rack that looked not dissimilar from this, full of power supplies, oscilloscopes, multimeters, signal generators, ground radios that allow you to exercise each component, subsystem, and system while it's being integrated. This is another thing that's often left too late, where if you say, well, I got a radio and I'm pretty sure it's going to emit at 915 megahertz, and so I'm good. Incorrect. We'll get to the tests in a minute where you actually need to prove that. Every satellite must have a dedicated electrical ground port where when it is fully integrated, you can activate the system, you can power it up, you can run your full functional tests, your abbreviated functional tests, all the way up until you are at the launch site, ready to stow it for the last time to confirm that it has survived every test, every transport, every integration activity, and is ready for a full mission success on orbit. This will typically give you connection directly into the flight computer, so you can boot it up, control it, override certain automated sequences, and run sort of those functional tests that give you a diagnostic to say, yep, it is ready to go. It's never flight representative, meaning it lets you override some of those automated things. It lets you SSH directly into your shell if you want to do that, which is much more difficult to do over RF. So it is also very important to run functional testing over the RF interface in the actual flight config to show that you can accomplish everything. Your software engineers will get very comfortable with the GSE port and will be quite upset when you take it away from them and make them do everything over the radio. For charging and discharging, we have to do that as a full up integrated test. And so we need a power port on the side that allow you to charge, discharge the batteries, monitor the batteries, maybe power things up around the inhibit switches, things like that, and make sure that your batteries are topped off, ready to launch. CubeSats are typically stored for a very long time prior to launch. So making sure you have the absolute maximum capacity in your batteries when you start, so that you'll make it through that storage period, which you will not be able to know how long that's going to be. COM interface, this is something I showed earlier where we had a patch antenna for one radio, but a hardwired coaxial connection for another one. When we do our COM tests, it's great to be as close to over the air as possible, but you'll never be able to simulate your satellite being hundreds of kilometers away through the atmosphere in space. And so we can either do that with little whip antennas like you see here, with coaxial cables and attenuation. So attenuating the signal to be representative of how much fade you're going to have. You can use hats, which are just a metal Faraday cage that can go around your patch antenna and allow you to actually radiate out of your antenna in a sensitive area where maybe that RF emission is not licensed or permitted. Something to consider. When you're in your full up integrated spacecraft config, this is as close as you're going to get to on orbit until you do this long range unsupported testing. Integration, the partner of assembly, but a slightly different flavor to it, where we're actually composing a system rather than assembling a kit of, does the bolt go in the hole? Does the bracket fit the bolt? Does the bracket fit in the structure? Does the structure fit in the dispenser? This is more, how is my system building up? So we're trying to methodically work our way up the V, where we're assessing the board subsystem component at its lowest possible level, test it, understand what it's designed to do and what it actually does. Write, check, execute our full functional test at that level, and then move on. Do not move on until you pass at the lower level. This is where the support interfaces come in, where they will actually affect behavior. So like really common example, if you have say a radio or a camera or something that communicates over a serial port, that serial port can actually power the system. So you could say, I have turned off, I have removed power, I have disconnected my power supply, but the system's actually still on because it's drawing power from your computer over the serial cable. And that's something that will not necessarily happen in the integrated configuration, and something to be very mindful of. How are my support interfaces changing and affecting the behavior of the thing under test? Then you build up this flat-sat, integrating those components and subsystems into a larger system, doing that as methodically as possible. Scientific method, never change two variables and remeasure, only change one variable at a time. That way you know what's actually causing the change in the outcome. Spending as much time as you have in your schedule at that flat-sat level is the most important thing of any system component. Like I said, it's so iterative. That takes so much time to learn, iterate, fix, and build. And all that time spent in that case just builds experience, builds knowledge, gives you the best chance of success. Of course, then you hit assembly and you're like, oh no, it doesn't fit. So getting through that iterative assembly process is very important too. The number one lesson that we all forget, and I do a bad job too, is to write down what you've learned, to document it, to put it in a notebook, to put it in Confluence, wherever you can, because you're not the only person that needs to know this. The next person who does the test really needs to understand what you tested, what happened, and why, so that they have the best chance of building on your experience. A really good integration sort of lesson learned that we have that was not an assembly problem, but was an integration problem is we have a global star modem in VPM in a number of our satellites. They're great, highly recommended, but they are an L-band transmitter. In most of our satellites, we have GPS receivers because we want to know where they are. GPS is a really good way to do that, and it is a receiver in L-band. So you can see where this is going from the photo on the right. Every time we used our radio to transmit the position of VPM, it would lose what that position was. It would break the GPS receiver lock on the constellation, and we would lose position. So kind of a really difficult catch-22 there. I want to know where it is, but if I tell me, then I won't know. So this is what's called an electromagnetic interference, or EMI, EMC issue, where those two systems performed exactly as designed and exactly as they were intended to when apart and under their component testing. But when we put them back together in the flat-sat config, we observed that one would impact the other. This wasn't a test we had planned. Seeing it laid out in this one slide, it seems very obvious, but believe me, they spent It took a lot of time to figure out what was happening. And you can see we actually ended up putting a spectrum monitor on the system of the GPS receiver to say, oh, look, here's the normal power spectral density of receiving a GPS signal, but when I transmit, I completely overload it. Didn't explode, so that's a good thing. This is a problem. So we need to actually do some iterative procedure assembly testing to understand and mitigate this problem. So we tried moving the antennas farther apart, and that didn't do anything. The transmitter is way too loud. We tried putting the receiver in a box to see, is it coupling between the antennas or is it coupling, on the like little actual circuit boards? And it was kind of mixed results. It was a little better, but still wasn't actually working. And then we were like, okay, well, we actually need to filter this signal out. So the transmission is on the very, very high end of the GPS band. So what if we, put some filters in there to get rid of it? And that is what fixed it. As we did this iteratively, we're like, well, it's already in a metal box, so let's put it there. Oh, let's get the SAW filter in there and use some of these kits to actually go and inspect the effects of each of those changes. So this is something that cropped up in integration, was not something we planned for. We identified, fortunately, because we were doing an integrated test and saying, hey, can I transmit my GPS position? No. And then here's how we resolve that. So you might not have that problem because I just told you about it and you'll plan for it, but you will have other problems that are like that. And so just being prepared in scheduling, programmatics, budgets, and mentally for how bad it's going to go will set you up for success. Software integration, my software cohort is not in the office right now. Otherwise, he could tell you much more about this. But software is equally as critical in the integration process as the hardware. The hardware is what you can see, what you can get hands-on and observe, but the software is what enables those tests to be run and enables those systems to perform. Often you can run scripted tests. You can actually integrate that into your software to be able to script and repeatedly perform the same test in the same way over and over and over again. So something like a charge discharge test, you could automate the power supplies and the electronic loads. Something like that GPS receiver test, you could automate the RF transmission so it's repeatable every time. It's not up to the human configuring the system. You can also use software to write logs, and you should use software to write your logs. That gets you records that are repeatable, reliable, write out the same data point every time. And that gives you a record all the way through your campaign to know, oh, back in February of 2021, we started seeing some deviations on this voltage. We're not really sure why. Let's go back and look at all our other data from around there and see what happened. Oh, it turns out Bob ran a test and he wasn't grounded and he broke something. That being said, software will not fix the human problem because, well, ChatGPT might help, but humans are still writing this software. So you still need to understand what you're testing, what your expected outcome is, and what your actual outcome is. The CubeSat community has a lot of overlap with the maker community, with drone pilots, drone builders. There's a huge microcontroller community out there now, embedded Linux community, and we get to take advantage of a absolutely massive knowledge base. And so there are things about this that are very unique to space, and there are things that are not at all unique to space, particularly when it comes to the software. And so that's something to leverage, take advantage of, and bring into your programs. But yeah, don't steal code. So you've assembled, you have integrated, and now it is time to test, although you've been testing all along the way there. So the 5 tests that the UNP program office mandates that are just smart to do are simulated or long-range comms, command execution, ADCS verification, charge cycling, and day in the life, the big one. So these are the things that prove that when you put your satellite into space, it will do the mission that you need it to do. So the simulated long-range comms addresses that issue I touched on earlier of 2 systems separated by a huge geographic distance being able to communicate over RF. The command execution validates that your software is capable of both running your mission and addressing faults, responding to all commands, and including off-nominal ones, and that they have the desired effect. ADCS verification proves that you can, if you have to, point your satellite where you want it to point, and that it can actually tell you that, so you know that your camera is aimed at Zimbabwe and not deep space because it's upside down. I've done that too. Charge cycling validates that your power can receive electrical energy from your solar panels. Typically, I don't think any of you have nuclear reactors. Put them into your batteries for when it gets dark, and that it can output that power to the system as it needs to. This also needs to include when you discharge your batteries that they will go into safe mode, that you will start turning things off in order to save power, because you might be tumbling, something might be broken, and you need to be able to get to a safe state. Day in the life validates all of those things and your ability to kind of perform your mission. So it's a sort of, it's more a week in the life. It's not exactly a day. It might take a day to run. It probably takes a week to run, where you power your system up and then start doing things, running compasses, taking pictures if your mission is to take a picture, measuring spectrum if you're doing that, whatever your mission might be, that you can actually perform all the steps and that the system can perform all the steps necessary to meet that successful mission objective. Other integrated tests that you have to do are a full functional test. So that's saying when I've gone through a vibration test or a thermal test, or I've carried it on a Southwest flight, that I have not affected the system in any way and that it still performs as expected. How do you test attitude control in a non-microgravity, full of friction environment? Great question. Let me know when you find out. As best we can. So we can do that at component level of saying, if I command a reaction wheel to spin at 2000 RPM, it spins at 2000 RPM. If I command a rotation about the Z axis, that I see the actuators that do that start performing what they should do. You'll see air bearing tables where you try to mount either the attitude control system or the entire spacecraft to as frictionless a bearing as we can get here in atmosphere, and command rotations. It's not perfect. This is definitely the hardest one to simulate the space environment because zero gravity is like really hard to get here on Earth. And typically it's good enough to do at the sort of component actuator level, integrated software level, to say, you know, if I command, all my polarities are right. So if I command a positive rotation, it looks like it's trying to turn in the positive direction. If I command a negative rotation, same deal. It's the most common failure I think that we've seen is actuators or commands get inverted, and that causes a whole host of problems. Really great question, and something that we're all actively looking at. Thank you, Paul. The abbreviated functional test onto the integrated tests is where we sort of do a quick, should be 10, 15, under an hour, to just check aliveness. That might be between axes of a vibration test, something like that. But it just makes sure nothing truly critical has broken, or like a connector has fallen out, or a bolt hasn't wreaked havoc. So onto environmental testing, our kind of final system level tests. These are what simulate the launch and space environment to ensure that your system will survive in the environment. We've kind of proven that it does what it's supposed to do, or at least what you designed it to do, that it's capable of, say, taking an image, storing it in memory, and downlinking it over a radio and having the power to do that. This is what makes sure it will get through the launch environment, which is mechanically quite violent, and then the space environment, which is thermally quite violent. So we do both vibration testing, thermal cycling. As you go through, you know, day-night cycles in orbit, you cycle the temperature quite dramatically. And then obviously you have to exist in vacuum forever. We can use a chamber to simulate both the vacuum and the thermal environment. And that's kind of what gets you the closest to space that your system's going to be in. So vibration testing, this is our facility there at AFRL. Like I said, we usually put them in the dispenser because that's the environment you're going to be in. Some dispensers are quite loose, which is quite frightening. The Cal Poly P-Pod is only marginally constrained, so you will rattle a lot, which is horrifying to watch, but actually dampens a lot of the sort of high G load, and it's actually a gentler environment despite how loud and noisy and frightening it is. A lot of the energy is going into noise instead of into your system, which is kind of a good thing. Some dispensers are extraordinarily rigid and will transfer all of the load directly into your mechanical structure. And so that's something, as you're making the choice between a tab-based structure or a rail-based structure, those are kind of the two choices you get to make early on. Those can wildly affect the loads that are actually going to get transferred to your satellite. but you should do a good enough job in your design to where it doesn't matter. It's not all that complicated to design for the absolute highest launch environment in the most rigidly coupled case that you will ever see, because CubeSats are nice, small little bricks, and they don't have a lot of big, flexible, resonant structures. You'll shake the system in all three axes. The launch vehicle, so SpaceX, Falcon 9, Falcon Heavy, the Vulcan, all of these rockets will have what their environment will look like wherever you happen to be mounted. You will be in a dispenser attached to a ring, attached to another ring, attached somewhere on the stack, and the launch provider will tell you, this is the load to expect, this is what you need to plan for, and this is what you need to test for. And this is how we do that, the big old table. How you tell that you've passed: number one, you pick up the satellite and shake it, and if anything falls out, that's a really bad day. That does happen. And then we can actually use a sign sweep test where we sweep through the whole sort of frequency range and observe our resonances and see if those have shifted during the random vibration test. Something has changed. Something has either settled or broken. Something has happened, and there are success criteria for how acceptable or how much those changes can be. Thermal testing is extremely important and very difficult to design for without many, many years of very detailed thermal analysis that'll still end up being wrong. So this is where we say, I can shed all of the heat or keep as much of the heat as I need to when I'm in vacuum, both in day and night, and keep all of my systems operating. Batteries are by far the most constraining in almost all systems. Batteries really don't like to be cold. And so making sure you can keep them warm enough, but without overheating all of your other components and, melting solder and things falling off is the name of the game. So we'll do a thermal balance test where you just put it in vacuum and turn it on and see what temperature everything hits. You'll cycle it to actually get that mechanical stress of heating and cooling, expanding and contracting all of your joints. And then thermal vacuum, where you'll cycle it in vacuum. And those are the things that find those material process workmanship defects that are only going to be present when you're in that full final environment. And this is where really you find the most fiddly, difficult, and nuanced problems. And so you'll typically do that towards the end after vibration testing. And that's kind of your last final, like, oh man, okay, if we pass this, we're good. But that's why I said plan for disassembly, because if you find something that late, you need to be able to go fix it and get back through all of these tests and prove that you are good. That is a really fast and really high level overview of what can end up being years of your life of assembling, integrating, and testing space systems. But it is really, really fun. It is really, really engaging and inspiring and my favorite thing of all time. And so I hope you all get the opportunity to participate in at least some part of it, because it is very exciting. And then you get to go to space when you're done.